channel is induced. We spend some time on that. Next, we're going to do, so if channel is induced, we can say the MOSFET is not operating in cutoff region. The MOSFET is either operating in triode region or in saturation region. For that, what should we do? We have to do VGD2, VGD2, okay? So, which is VG2 minus VD2. VG2, we know that's 0, VD2, but we don't know VD. We don't know VD2. We have to determine. So, in that case, what we did? We go for assumption. So, assume saturation. Okay. If you assume saturation, we know the current ID Kn VGS2 VTN whole square. Also, like we do a couple of more programs, same problem. We know that ID, we are going to have two variable, another ID and VS2. I have to find another equation with the same two variable, and in that case, it should be VS minus, which is minus 2.5 minus 2.5 divided by RS, so which is equal to 1. So after plugging this value, I'm going to get a quadratic equation, and what I'm going to get VS2. আমি VS2 টা আমি এটা নিয়ে আর ইয়ে করলাম না, VS2 দুইটা ভ্যালু পাবো, একটা হচ্ছে VS2 বলে আমি এখান থেকে নিয়ে আসি, VS2 VS2 after calculating the quadratic equation, of course RS is equal to 1K, must. So it is going to get VS2 is minus 1.652, another ones 0.518 volt. Last class we learned that what I'm going to do, I'm going to do VGS, plugging both the value. In that case, if you select VS2 is equal to minus 1.652, only then a channel is induced. If you plug this value VS minus 0.518, it is less than VTN, channel is not induced. So that gives us VS2 V1 equal to VS2 is equal to minus 1.652 volt. V1 পেলাম, তারপর I can determine ID. So ID এর জন্য we know that ID is equal to VS2 plus 2.5 divided by RS. So ID is equal to VS2 plus 1K, which gives us minus 1.
স্যার এটা V2 হওয়ার কথা না, V2 equals to VS2.
এটা কি নিচে কি V2 ছিল? ঠিক আছে, সরি, it's my mistake again, sorry. Okay. V2 here. 2.5 divided by 1, and the current value 848 milliampere. So that is our drain current. So that's what it was written earlier. 848 milliampere. Okay. Now, so we obtain the current ID assuming that it is operating in saturation region. For that, after doing that, what should we do? We need to justify. For justification, we need to do what? We need to do VGD. So VG2 minus VD2. But again, we don't know VD2 yet. So therefore, I can't justify this right now. I have to, that is for first of all, I have to determine VD2 to do the justification. Okay. So how can you determine VD2? That is our VD2. Sorry, VD, no, VD, yeah, VD2, which is our V1, VD2. This is our VD2. So this is our VD2. I have to determine VD2. Acha. So how can you determine these things? For that, what I'm going to do, if you look at the MOSFET 1, MOSFET 1, the gate is connected to 2.5 volt and the drain is straight away connected to 5 volt. Okay, then there is a current flowing which is 0.848 milliampere. So since a current is flowing, so channel must be induced. So for MOSFET, for M1, ID equals to 0.848 milliampere. So channel must be induced. Channel must be induced. So therefore, if channel is induced, no certain, no confusion about the channel being induced or not. Next, we have to do what? VGD1 to check if the MOSFET is operating triodies or in saturation. So VGD1. Let's do this. VG1 minus VD1, which is 2.5 minus 5, which is minus 2.5 volt. Okay. So that it's less than VTN. So that means no channel at drain end. No channel is drain end. So it must be operating in saturation zone. It's operating in saturation region. Okay. If it is operating in saturation region, then I know the current that we have already calculated, ID Kn VGS1 minus VTN whole square is equal to 0.848. Okay, after plugging the value, we're going to get Kn, which is 1.5 VG1 minus VS1 minus VTN whole square 0.848, where 1.5, it is 2.5, VS1 unknown minus 0.9 whole square 0.848. And if you calculate it, you're going to get VSN1, two values again. One of them is 0.848. Another one, let me find it from the problem there. Another was 2.5351. So 2.351. So 2.351. কোনটা রাখবো? So again, we're going to do VGS1. Okay, so VG1 minus VS1. So VS1, if you use this value, we get no, if this value, so it is 2.5 minus 2.351, right? Less than VT1. That takes us no channel. So that takes us to cutoff, which is not possible because we already know the current is flowing. So that means this one must be a right value. So I know VS1 equal to 0.848. That is what? VS1 0.848. What does that mean? It is, in fact, is our V1. Also, it is in fact our VD2 তাহলে আমি VD2 পেয়ে গেলাম of course voltage now I'm going to use this VD2 to check if a channel is induced or not in the first channel at the channel at sorry just for justification so what should I do VG2 is 0 for MOSFET 2 minus 0.848 which is clearly less than VTN that is no channel at the drain end so it's saturation region saturation okay so these are the value V1 equal to 0.848 volt and V2 equal to minus 1.652 and ID is equal to 0.848. So this is the okay. So I'm going to solve. As I have already said, I'm going to solve one of these problems, and just I'm going to give you this problem and another problem to try to solve. Take that. So next topic is a BJT. What is BJT stand for? BJT stands for bipolar junction transistor. Just a second, please. Okay. So we say that there are two types of transistor. One is MOSFET, another is BJT. The reason both of them are MOSFET because they share the same characteristics. Their operation principles are different, their construction is different, but their characteristics are same. So what are the characteristics? If you look into the characteristics of BJT, it looks like this. Sorry, MOSFET. If the drain current is ID, and if you apply drain to source voltage, we found out that the characteristics such that as you change the drain to source voltage, there are two parts in the characteristics. Once the current is while the current is increasing, so from here up to that part, you say the current is increasing. After that, current remain constant. You're going to find out that exact same characteristics. So let's say we call a current IC, right? Collector current, and we call it current VCB. We're going to find later. So as you are changing VCB, you're going to find initially, sorry, VC for VC, initially current is increasing and then current remain constant. So because of these characteristics, we can use the transistor for different purpose. We're going to use the device based on their characteristics. Okay, so we're going to find out that I can use it for amplification purpose. I can use it for switching purpose. Take that. But what first of all, then we're going to start. We're going to start with the construction. BGT is a three terminal device. Okay, it consists of it's a three-layer device, and the layers are of alternating type. Three-layer device: layer one, layer two, and layer 3. So layer 1, 2, and 3. It's a three-layer device, and the layers are of opposite alternating type. That means if it is our N-type material, then it is our P-type material, and the next one is P-type material. So that is one possible combination. What could be the other possible combination? It could be P-type, then it is the next one is N-type, and the other one is P-type. So the the layers of alternating type materials, when they put together, it becomes a MOSFET. So that means there are two types of MOSFET available. One of them is called N-type, NPN type, sorry, NPN type. Another one is PNP type, depending on how which material that you use. Mostly we're going to discuss about the NPN type, and just NPNP type is just a logical extension of NPN type. Now, if you take three terminal out, terminal 1, terminal 2, and the terminal 3, that completes the device. The, the terminal on the left, it is called emitter. Emitter. The one in the middle is called base, and the third one is called collector. Okay. So in short, we're going to call E, B, C, emitter, base, and collector. And the region next to the emitter terminal is called emitter region. The region next to the base terminal, or the base terminal is connected to its base region, and the region where the collector terminal is connected to is called collector region. Okay, so we're going to learn soon why they are called so. Now, if you notice, the N, if you notice, between emitter, which is N-type material, and the base, which is P-type material, there is a PN junction. We have a PN junction. So PN junction means we have got a depletion region. And in the N side of the depletion region, we have layer of exposed phosphorus ion. On the P side of the depletion region, we have layer of exposed boron ion. So we have a depletion region. Similarly, the collector, N-type collector, and P-type base on the other side, they make another PN junction there. So that means we've got another depletion region. Again, exposed boron ion and exposed phosphorus ion, positively charged phosphorus ion. So this junction, it is called emitter to base junction, and the other junction, it is called collector to base junction. So that means a BJT is nothing but two PN junction connected back to back. That means if I model it, let's say if I model it, simplified, approximated way. So the piece base to emitter, we have got a diode. Again, base to collector, we have got another diode. So that is our base. Sorry, this is our emitter, this is our base, and this is our collector, and that is our emitter to base junction, and there is a collector to base junction. Okay, so the construction of the BGT can be represented by two diode connected base to base, connected back to back. ঠিক আছে? Now, why do you call the emitter as emitter region, the base is base region, or the collector is collector regions? First of all, emitter side, it is heavily doped. That's why it is, you know, represented N plus. That means concentration of electron is very high. Base, lightly doped. The concentration of hole in the base region is not that much. You can say not that much. So sometimes you put it P minus. And also base region, you have noticed, it is narrow. Narrow in width compared to emitter region and the collector region. And finally, the collector, it is neither heavily doped nor lightly doped, so normally doped. So this is the doping profile of each region. Emitter heavily doped, collector base lightly doped, collector normally doped. Okay. And on top of that, the base region width-wise, it is narrow compared to the emitter region and the collector region. Okay. Now, why do you call emitter as emitter? Emitter emits electrons. Emits. So since this is rich in electron, so the when you apply voltage, what happens is that emitter emits electron into the base or inject electron into the base. Emitter emits electron or inject electron into the base region. Okay. So from there, you will say some of the electron will go to the collector region. So emitter emits, the collector does what? Collector collects electron. Collects electrons emitted by the emitter. So emitter emits, collector collects. Then what is the role that the base play? Base controls the flow of electron from emitter to base. Base controls the flow of electron from emitter to base. If you remember, when we were discussing MOSFET, we said that the channel region does what? Channel region is essentially a region where you can change the conductivity. We can tune the engineer or tune the conductivity. I can make it conductive. I can make it absolutely non-conductive. And we represented these things using water tap model. So let's see if I draw in water tap. Okay. So we have got a bucket, and this side is like our emitter. Where water is from, where the water is coming in. This is like our collector where water is coming out. Collector, emitter emits, collector collect. Okay. And then we have got a key of the to the tap. That is like our base. So the position of the key decides what is the amount of water should come out from the supply main to the collector. If it is all the way closed, no water. If it is all the way open, maximum amount of water. So base does the controlling, says just the control. So this is control. So we can say, I have just, we can say, let's write it down. আচ্ছা আমি লিখি. So if you use the water tap analogy, water key closed as if high resistance. It is no current, no electron flow, so high resistance, like as if it is high resistance. High no flow of electrons from emitter to collector if it is closed. So same thing. If base is if you apply it, if the base is controlled such that if it is such that it is closed, no flow of electron from emitter to collector. If it is all the way open, it is like very low, high conductance. Okay. Use flow of electrons from emitter to collector. The same thing. So that means, so base by you can by controlling the base, you can control the conductivity between emitter to collector. So like same thing we did. So something remember that. So let's say this is our emitter region, and you have this resistance, and this is a collector region. So emitter, like and collector. So we have emitter has a huge storage of electron, okay, and it can collect. So if you're applying a third terminal, which is base, if you control the base, you can make it very much conductive. You control the base such that it become resistive, no current display. We did the same thing. We learned the same thing for uh, MOSFET. So when it's make an analogy, so in base is very much like the gate for MOSFET, and emitter is like the source for MOSFET, and collector is like the drain for MOSFET. Okay. So this is what they do. Now, so we already said that if you have an NPN type MOSFET, you can also have PNP type MOSFET. Just very briefly tell you what they look like. So for PNP MOSFET, so let's say this is the construction. Emitter, base, collector, P and P. Okay. Again, two junction, emitter to base junction and collector to base junction. So, so here what it does, emitter emits whole, collector collects whole. So emitter emits whole and collector collects, and base controls the flow of electron. So everything remains the same as in NPN. Only thing is that in NPN it is the electron which is emitted, and in PNP it is the hole that is emitted. What is the two diode model? The two diode model looks like this. Okay. Between P side and N side, we have got one diode. Between this collector and base, we have got another diode. So emitter, base, collector. This is our emitter to base junction, collector to base junction. Okay, that's it. So next topic is symbol, BJT symbol. BJT symbol looks like this, typical BJT symbol. Okay. Of course, you can logically say the middle one, the three terminal middle one must be what? The base. Then question is which one is collector, which one is emitter? What is the thing? You see, there are two terminal. One of them has got an arrow. So the terminal which has an arrow is emitter, and the remaining one is must be collector. So base, collector, and emitter. Now, the arrow in one terminal does more than identifying which terminal is emitter. It does more. Number one, arrow gives you the direction of the current. In any MOSFET, same as in MOSFET, where there are voltage in three terminal, but unlike in MOSFET, where there is only one current component that we have to deal with, uh, in BJT, each terminal there will be one current. So in the base terminal, this current is IB. In the collector terminal, this current is IC, and this is the emitter terminal, this current is IE. Whereas in MOSFET, there's only one current. This is a good thing about MOSFET. So if you compare, you're going to find out, if you compare uh, the maths or the circuit analysis between MOSFET and BJT, MOSFET is far simpler compared to BJT, because in MOSFET you have to deal only one current. Why? Because the gate current is T. Gate current is 0. So three terminal device, if one current is 0, so that means we have essentially only one current. However, this is not the case for BJT. BJT has three terminal, three current, three current. Now the question is, which direction the current will be flowing? Current always flows in the same direction where the arrow is pointed. এটা just copy করে নিয়েছি. Okay, I think it has got it. Yeah, arrow. Current. All the currents point towards the direction of the arrow. So that means the base current flowing the same direction as the arrow, collector current, the same direction as the arrow, emitter current, the same direction as the arrow. Okay, so that means in that case, we can see the base current is entering the device, collector current is also entering the device, but the emitter current which is leaving the device, So if you apply KCL, we can clearly find that IE equals to IB plus IC. This doesn't tell us what types of BJT it is. Is that a NPN BJT or PNP BJT? Okay, again, this arrow tells us the story. Arrow always points from P side to N side. Always pointed from P side to N side. So that means in the arrow of a BJT, it is starts from the P side, the head is always on the N side. So that means it must be the NPN GT. It's NPN BJT. Okay. So now this way, so how can we draw the PNP BJT? So PNP BJT. Okay. So that is our base. This must be our emitter. This must be a collector, and this is the current. The same direction like the arrow, IE, IB, IE and IC. What does that mean? For PNP BGT, emitter current is entering, they're pointing in the same direction as the arrow. Base current leaving, collector current leaving, same relationship holds for both cases. IE is equal to IB plus IC. Then again, arrow tells us what? This must be our P side. This must be our N side. So that is PNP BGT. Okay. So now we learned the basic construction is symbol. Next, we are going to find out the region of operation. The region of operation. For MOSFET, we know that MOSFET operates in three regions: a cutoff region, triode region, and saturation region. Okay, so cutoff region, triode region, or in saturation region. So similarly, the BGT can have three or multiple region of operation. How can you determine which region the BGT is operating? Okay, so let me draw. So let's say we take a normal diode. We take a normal diode. So we have got a diode. And then let's say voltage, the voltage sector of the diode is VD. And the current through the diode is ID. Sorry. Oh, it's not. Okay. So we have got a diode. And you are asked to bias it. So how many we can bias it? If you have one diode, there are two ways you can bias it. Either you can make it what? Forward biased, or it can make it reverse biased. What does that mean? So that means you have to apply an external voltage such that P side is connected to the positive terminal, N side is connected to the negative terminal. That is a forward biased. Okay, or you can apply a DC voltage such that P side is connected to the negative terminal, N side is connected to the positive one. That is our reverse bias. That is, but if you have another diode connected back to back like this, and then I want to, okay, so I call one of them is EBJ, another one is CBJ, and I want to bias the two BGT at the same time by two separate voltage source. How many ways we can? What are the possible combination of biasing? Can anyone tell me? So let's say this is our emitter, this is our base, this is our collector. So there are, if you have one diode, there are two possibilities. If you have two diodes, how many ways we can bias both the BGT? What are the possible combination? কে বলেন তো কেউ?
Sir, if I flow the
Again, I
current
guess
from base, it
I'm
will
not
be
I'm
followed
not
by.
talking I'm not talking about the current flow. I'm just talking about you have one diode. There are two ways you can bias it. Either you can make it forward biased, you can make it reverse biased, and then you have two diodes next to each other, and you want to bias it at the same time. How many ways? What are the ways you can apply voltage? What are the possible ways you can apply voltage to bias each of them? How many possible ways you can apply voltage? I'm just simply asking. What are the possible ways?
স্যার দুইটা পসিবল ওয়ে হতে পারে।
একটু জোরে বলেন।
দুইটা পসিবল ওয়ে হতে পারে, মানে দুই জায়গায় মনে করেন পজিটিভ দিয়েই দুই জায়গা দিয়ে ফ্লো করবে, তাহলে ফরওয়ার্ড বাইস।
না, পসিবল ওয়েজ টু অ্যাপ্লাই ভোল্টেজ টু bias both the diodes simultaneously. Whether for forward and reverse, both the bias, forward reverse. কেউ পারেন না? I'm saying possible ways to apply voltage. এই এখানে কয়েকটা ওয়েতে আপনি ভোল্টেজ অ্যাপ্লাই করতে পারেন। আচ্ছা, one way is that I can make it forward biased. I can apply voltage such that emitter to base junction forward bias, and I can apply another voltage which is forward bias. So I have forward bias. There is one possibility. I have reverse bias, another possibility. I have forward biased here, reverse biased was third possibility. I have reverse biased here, forward biased here, fourth possibility. There are four ways. Okay, let me explain to the table. So let's say we have got this table. I call it EBJ, I will CBJ, and we call it region of operation. Okay. So what can I do for EBJ? I can make it forward biased, and then I can also make CBJ forward bias. Remember, when I say I am making forward bias, I'm applying an external. So I'm saying how many apply? I am applying an external voltage here, another external voltage here. It doesn't have to be same voltage. It could be different voltage. So when I have this terminal E and B, I can apply a voltage such that it is forward bias. I can apply a voltage such that it is forward bias. That's one possible combination. So this is called this. When this is happen, this is called saturation. That's one possibility. What is the other possibility? I can make it emitter to base junction reverse biased. Emitter to base junction reverse biased. Also, collector to base junction reverse biased. That's another possibility. Do you agree? That is cutoff. Third is emitter to base junction forward biased and collector to base junction reverse biased. That is third possibility. That is known as forward active. And the fourth one is emitter to base junction reverse bias, collector to base junction forward biased. This is called reverse active. It is goes by 2 to the power n, 2 to the power 2 to the power 4 possible. So this is the four possible ways we can apply voltage. Now notice this has got a similarity. So we have, it is not the first time that we are observing it. We have already seen it for MOSFET. So what is the corresponding? So for MOSFET, so equivalence to MOSFET. So MOSFET equivalent saturation region in BJT is the triode region, equivalent to triode region in MOSFET. Cutoff region in BJT is the cutoff region in MOSFET. Forward active in BJT is like the saturation region and MOSFET, and reverse active, it doesn't have any equivalence in MOSFET. In fact, the BJT is not designed. Of course, theoretical possible to make it reverse bias, but the BJT is not generally designed to operate in the reverse active region. So from now on, whenever I'm going to say the forward active, instead of saying forward active, I'm just going to say active. If I say active, it really means forward active, not the reverse active, because it doesn't have any action. ঠিক আছে? So again, when both the junctions are forward biased, it is our saturation. When both the junctions are reverse biased, it is our cutoff. When emitter to base junction forward biased, collector to the base junction reverse biased, that is our forward active. What is the application? If the BJT is operated between cutoff and saturation, it can be used as switch for switching operation. Same thing we saw for MOSFET. When the MOSFET is operated between triode and cutoff, they have switching application. In MOSFET, when the BJT is biased to operate in the saturation region, it can be used for amplification purpose. Amplification. Same thing, if you want to amplify any signal, you have to bias the BJT to be operating in the forward active region. So these are the operation. This is the operation, switching and amplification. So next we see what happens in forward active region. So I'm not going to exactly say what is going to happen, what's physics behind it. I'm going to see what we are going to find. Okay, so let's say we have got an BJT represented in their approximate model. Let's say emitter, base, collector. This is emitter to base junction. This is collector to base junction. I want to see active region. Active region. What happens in active region? Okay. So I apply the voltage such that emitter to base junction is forward bias. So let's say we apply the voltage VEB. So VBE. So plus minus. And then we apply voltage VCB. So plus minus. তার মানে কি দেখেন, P side is connected to the positive terminal, N side is connected to the negative terminal. So it is forward bias. And here P side is connected to the negative terminal, N side is connected to the, so it's reverse. N side is connected to the positive terminal, so it is reverse bias. So now I can say it is what? It is operating the forward active region. So if this is the case, a current should be flowing. We already know the for NPN BJT, the emitter current is leaving the terminal. Base current is entering the terminal. Also, the collector current entering the terminal. You see, emitter current leaving, base current entering, collector current entering. Okay. Now, how the current that is flowing emitter terminal, base terminal, and collector terminal related to the voltage applied between base and emitter and collector to base? Let's find out. For that, let's consider a single diode, just very simple diode. The current that is flowing is ID, and the voltage that we apply is VD. So plus minus. We already learned according to diode equation, ID equals to what? IS e to the power VD over and VT. And if we consider N is equal to 1, that we get IS e to the power Vd over Vt. Then that means I can say ID is according to diode equation, ID is proportional to e to the power Vd over Vt. Okay. So which means if you increase change ID, change Vd, you're going to get ID. So that is nothing new. This is the IV characteristics of diode. ID, Vd. So if you change Vd, you get changed ID. You get changed Vd, you get ID. So ID Vd change করলে আমি ID পাচ্ছি, different ID পাচ্ছি. So ID is proportional to Vd over Vt. Now notice here, what do you have here? We have got a diode which is EBJ, which has got a current flowing here IE and a current flowing here IB. And then we have CBJ, we have got a current flowing here IC. And then we have voltage across EBJ is VBE and the voltage across CBJ is VCB. So I can easily apply the diode equation for that case, in which I can say IE, which is the diode current, IE, which is the diode current, isn't it the diode current? It is coming out of the diode. It must be proportional to VBE over VT. IB, it is also diode current. So it must be proportional to e to the power VBE over VT. And then my question to you, what about IC? How can I write IC? What it is dependent on? Can anyone?
VCB,
IC is equal to IC proportional to e to the power
VCB by VT.
CB by VT. It looks like this. Interestingly, it is wrong. Number one, IC is also, so in that case, IC, important here is IC is also proportional to e to the power VBE over VT. So that means all the current component, emitter current, base current, collector, all of them depends on only what? Only one thing, that is VBE, not VCB, not VBC. So not only that, particularly it's not only it depends on VBE, it is independent of VCB for VCB greater than minus 0.4 volt. So not only it is independent of VBE, it is also, sorry, not only it depends on VBE, it also independent of VCB. What does that mean? তার মানে হচ্ছে if I change VBE here, we're going to change IE here. If we change VBE here, we're going to change IC. We're going to change VB here. We find IC is changing. This one I can accept it very easily. IB, IC, IB and IE changing with VB, that I accept. But what is hard to accept is that IC, which is happening far away land, is yet it is dependent on VBE and independent of VCB. Okay, so that is the characteristics of BJT in activism, and particularly for which reason, like this, it looks like this. So in fact, if I draw the IV characteristics of BJT, then you're going to find out. You're going to find out this. If this is our IC, collector current, and this is our VCB, that means we voltage apply the voltage. You're going to find the IV characteristics look like this. Okay, so that is our, this is where the changing, again IV characteristic consists of two parts, one changing, one constant. That happens at a minus 0.4 volt. So any value to the right, it is active region. Why? Because VCB is greater than minus 0.4 volt and current doesn't change. Current কি change হচ্ছে? Current doesn't change. Any value, when the changing occurs, it's independent. So independent, no change of current. Okay, it is our saturation region. From 0 up to minus 0.4, saturation region. Saturation region. So what does that mean? We can find the current is independent. So that means everything that is happening is decided by what? Base to emitter voltage. ওই যে বললাম না, this is like the key here. Water tap, this is like our VBE. This is what is our VBE. এখানে VBE চেঞ্জ করলে আমার কালেক্টর করে এইটা VBE চেঞ্জ করলে আমার এটা উপরে উপরে ওঠানামা করে. You can imagine if I change VBE, that goes up and down, thereby changing the resistivity of the region. VBE যদি বাড়াই, সো তার মানে হচ্ছে এটা অন্য কারোর উপর ডিপেন্ড করে, ডিপেন্ডস অনলি অন so that means now if you notice the characteristics of the BJT for active region between base and emitter, it's like a PN junction diode which is forward bias, and between base and collector is like a dependent current. It is current source because current is constant. We are applying VCB, but the VCB is not changing the current. So current is independent of VCB. So current must be, it's a current source. So between the observing it, so base and emitter, a PN junction diode. Which is forward biased. And base and collector, or base and collector to emitter, finally it comes as a current source. It's a dependent current source. So combining these two characteristics, combining the two observation, finally I'm in a position that I can draw the model for BJT in active regions. So base and emitter, this is our EBJ, which is forward bias. Okay, plus minus forward bias, and the current flowing is here IB, and between emitter and collector to emitter, it's a dependent current source, which is IC, which is IS e to the power over VT. Okay, and this is our collector, current is IC, and if we already know that IC plus IB is in fact our IE. So that is our IE. So that is a large signal. We can say this is the large signal model. Large model অথবা DC model. DC of BJT. BJT. That means you see the behavior of BJT in active region is can be represented simply this way: base between base and emitter, base and emitter PN junction diode, and collector and emitter a dependent current source. Put them together, we get the model. So the behavior of BJT in active region can be represented using. Of course, you can draw the same model for PNP. If it is, let's say, PNP BJT, B2 in base emitter, it has to be forward biased. So I have to draw this. Base, collector, emitter, মনে রাখবেন P and P, this is our P and P, this is our N, this is our P, so this is our also P, emitter P, base N, collector P. So তার মানে if I have to make forward bias, how should I apply? This is our EBJ. How should we apply voltage? It should be applied VEB. Emitter side must be higher to make it for us a plus minus. That's why the diode is P to N. Acha. Current, emitter current enters the device. Collector current leaves the device. IC to IS e to the power VEB divided by VT. And this base current leaves the device. Maybe IC. So this is large signal model for PNP BJT. ঠিক আছে? Any question?
স্যার কুইজের খাতার ব্যাপারে স্যার কোশ্চেন ছিল স্যার।